Okay, hi guys. As promised, here is the thermochemistry refresher from Gen Chem I. We're going to talk about enthalpy. So let's start off with, what is thermodynamics? It's the study of energy and the conversions of energy. So there are some laws of thermodynamics that we're going to go through, but the first law of thermodynamics is the law of conservation of energy. And you probably remember it as being stated, energy cannot be created or destroyed, just changed from one form to another. So the nature and the classification of energy, that's something that we want to talk about. So energy is the ability to do work. Work is a force acting over a distance. So if energy equals work, force over distance, then work is equal to force times distance. Kinetic energy is this energy of motion, and that's one of the ones that's more common that we can understand. Thermal energy is a form of kinetic energy, and as molecules gain thermal energy, they start to move faster, right? And that means that as temperature is rising or lowering, it's the measure of the motion of particles. Potential energy is something that we refer to as stored energy or the energy of position. So let's think about forms of energy again. If you look on the left side here, you've got the gummy bears. And you may have seen this experiment before where you take the gummy bear and you throw it into, I think it's potassium perchlorate, and the sugars cause this wonderful glow, right? And we can all ooh and ah over that. But what that is the stored energy in the gummy bears, the bonds in the sugar, that is now being broken down on the right-hand side, and you get that release of energy, right? That kinetic energy. So our measurement of energy is the units that we measure. Calorie was the original unit. Joule is the standard unit, or the SI unit. So there's a conversion of 1 calorie is 4.184 joules. The calories that we're talking about, the little calories, are not the same. The calories in food are actually the big C, and that is actually equal to 1,000 calories in terms of energy. So heat, right? Heat and temperature. Heat is the energy exchange between, and when we start talking about this, we talk about systems and surroundings, right? So we usually have an enclosed system, and we talk about how the surroundings affect it. So when that heat exchange occurs, there needs to be a difference in temperature. Temperature is that measure of the thermal energy in a sample, right? So higher temperature matter, the heat is going to flow from that high temperature matter to a low temperature matter till you get to an equilibrium condition, thermal equilibrium condition. So it's a little bit like, looking at properties in mathematics. The zeroth law, right, of thermodynamics. If two thermodynamic systems are each in thermal equilibrium with a third one, then they're all in thermal equilibrium with each other. So we have to define system and surroundings. The system is the material or the isolated product or the isolated something that we're studying, and we're going to study the energy changes. We define the surroundings as everything that is surrounding the system that the system is in contact with. And so we study the exchange between the system and surroundings, and the total amount of energy between the system and the surroundings doesn't change, right? It just is transferred from one place to another. All right, 2 ways we can deal with heat transfer. If the temperature change occurs in a system, the heat capacity of an object, right, is proportional to its mass and to its specific heat. So certain materials absorb heat more easily, we know that, right? So the delta T, or the change in temperature, is the temperature final minus the temperature initial. So the specific heat capacity is the amount of heat energy required to raise the temperature of 1 gram of that substance 1 degree C. Okay? So now we can come up with an equation, and this equation on the right-hand side here, where we've got the heat, right, in terms of Q now, and it's in joules, right? It is equal to the mass times the specific heat times that delta T. Okay. We can take that from an object to now an equation, right? Or a reaction, a chemical rearrangement. And so now we can look at the delta H of reaction, right? And the heat that we talked about before, that heat of the system, is now equal to the number of moles times the delta H of the reaction. No temperature change here, but a change in energy. So specific heat capacity, again, it changes according to the element. Here's a bunch of elements and their heat capacities. Here's water. Huge, right? 4.184. Specific heat capacity of water is very large. And so different materials have different heat capacity. So now we can look at things like, okay, if we have a certain amount of a material, copper penny, right? And we've got a mass, and we know the temperature differential, and we can look up the specific heat of copper. How do we do this? Well, we take that Q equals mCT, mc delta T, right? Temperature final minus temperature initial, it rises from minus 8 to 37, so 37 is the final. So now we got 37 minus a minus 8 gets us 45. Plug that in, plug in the specific heat, plug in the mass, and boom, you've got the joules. So another way we can work this is energy transfer, right? Because the system, if the system gains or loses energy, it comes from or goes to the surroundings. And so the Q of a system is equal to the negative Q of the surrounding. So how can we apply this? Well, you got this block of metal, right? 55 degrees C, submerge it in water. Initially the water is 25 degrees C, energy transfer. It's going to go from the metal to the water. The temperature change depends on the mass of the metal, the mass of the water, and specific heat capacities. And it can all be set up this way, right? The final temperatures are going to be the same, right? The initial temperatures are going to be the things that may differ, right? The mass of the metal, mass of the water, the specific heat capacity of the metal, and specific heat capacity of the water, right? Those are the differences in those two equations. This is the surroundings, right? Because you drop the piece of metal into the water. Quick example, right? Mass of iron that cools from 78.6 to 21.4 in 375 grams of water. Heat capacity of water, heat capacity of iron. Water goes from 18.6 up to 21.4. Again, these final temperatures are going to be the same. That's something to keep in mind as you work through these problems. And here it is worked out, right? Plug everything in and you get 171 grams. Okay, so now if we talk about enthalpy, right? And we talk about enthalpy of a system, it's the heat content of that substance at a constant pressure. Delta H is something called a state function, meaning that you don't have to know beginning and ending, you just have to know the difference. That's why it's always delta, right? But if we can estimate these and come up with a delta H, we can do that by saying the reaction, right, at a constant pressure, right? The heat at a constant pressure, and constant pressure just means that if you've got some involvement of pressure changes that could change this system, that could be a problem. But this is the heat, right? And the delta H is going to be equal to that as long as we hold some things constant. The delta H, right, is just the final minus the initial. So is there a way we can estimate these finals and an initial? Well, it turns out we can tell the direction, right? And so if heat is released by the system, and we know it's exothermic, and we know that it's a negative delta H. If heat is being absorbed by the system, we know that it is endothermic, and it has a positive delta H. So we can relate these back to the components of a particular system, right? So in other words, if we look at something like the heat given off by propane burning in oxygen, right? And we know that it gives off 20 or negative 2044 kilojoules. We can say, okay, the delta H of reaction for 1 mole of C3H8 is negative 2044, but for 5 moles of oxygen, it's negative 2044. This is now an equality, right? And so these two equalities can be converted to fractions, right? Or conversion factors, okay? So now we can take equations, and if we know components of the equations, then we can determine the heat transferred, okay? And we can also determine what direction. So if we say when 2.45 grams of NO2 decompose, right, what is the heat transferred? Decomposing means it's going in the reverse reaction, or the reverse direction of the reaction that we just looked at. We know that the delta H for that reaction we just looked at was a negative 114. Well, when you reverse it, it becomes a positive. So here we've got the positive 114. We know that 2.45 grams is a mass. We've got to convert to moles. We also know that 2 moles, right, of NO2 is converted, because in that original reaction, right, it was a 1 for the NO. And so now we've got 3.04 kilojoules. So when you multiply a reaction, now we're going to work through a few of these things. When you multiply a reaction, then the delta H of reaction is just multiplied, right? So if, for instance, you start off with this carbon plus oxygen going to CO2, and you get a minus 393, if you double that, multiply the whole thing by 2, you get this minus 787. If the reaction is reversed, the sign is changed. We just looked at that. So one of the things we looked at before is Hess's law. There are a lot of Hess's law that we can look at, but the Hess's law we want to look at now is the delta H of reaction, right? And so the delta H of reaction is made up of the components of that reaction. So if we want to determine, for instance, the delta H of reaction for C2H4 going to C2H5OH in water, and we have these two fundamentals, right? How can we put them together? Well, we see C2H4 on this side, but we see C2H5OH on this side as well, so we got to reverse it and put it on this side, so that would make this a positive, right? and then go through and cancel out everything that doesn't stay in the equation, and you're going to come up with something that has this overall reaction. Add it together, right? And so when you add the delta H's together, you're going to get the delta H. Again, reverse that one and add them up, and we'll get to this delta H eventually. Right, so we're now crossing out things that appear on both sides. We're getting to this final equation. We get to that final equation and add the two delta H's together, and it turns out to be minus 43.6. So a little practice, right? What about this one? Well, you see, again, you see copper on the left, copper chloride on the right in this first one, and copper chloride on the right in the second one, right? So you're going to have to somehow get this copper chloride has to stay, this copper chloride has to move to the other side. So we're going to reverse this reaction, right? And then we're going to see how things add up. Okay, so reversing and crossing everything out, we get to the actual reaction where it's a delta H of plus 170. So standard state, we go back to the idea of standard state, STP. Gases at 1 atmosphere are standard state. A solid does not enter into the equilibrium. Substances in a solution with a concentration of 1 molar are at a standard state. That would then allow you to calculate the standard enthalpy change. And those are the kinds of things you'll find in enthalpy tables. So here's a standard enthalpy table that we can use, and we have used. Okay, Hess's law can be summarized this way in saying that the delta H of a reaction, right, is a summation of the delta H of formation of the products minus a summation of the delta H of formation of the reactants. And don't forget, we have to use the molar quantities, right? So stoichiometry is still involved here. All right, an example of that, enthalpy change in that reaction, we could go back and instead of adding two equations together, right, we can simply look at these formations. So the delta H of formation of CO2 given here, of H2O given here, of C2H2 given here, and of O2 given here. Delta H of formation of any element or diatomic is always 0. And so here is Hess's law in action. These are products, right? These are reactants. So it's the summation of the products minus the summation of the reactants. You get that overall.